Hello, good morning, and welcome to Scientists in Action, Hidden Gems. I'm your host, Kate, and I'm the Virtual Programs Coordinator here at the Denver Museum of Nature and Science, where we are broadcasting live from about 22 feet below the surface of the ground. That is right, we are broadcasting from the geology collections here below the museum, and I have with me today an amazing scientist that we'll talk to in just a minute, Dr. James Hagadorn, one of our curators of geology. So, hi James, welcome to our collections, folks. We're so glad you're here. One thing I want to go ahead and take care of before we get jumped into our program today. First and foremost, I'd like to respectfully acknowledge that the Denver Museum of Nature and Science is built upon grounds traditionally stewarded by the Cheyenne, Ute, Arapaho, and Ashato-Chacon nations. Likewise, we have students joining us today from not only Colorado, but I believe New Mexico, Arizona, Alaska, Washington, and Indiana, I want to say. So thank you everyone for joining us. We are so excited to show you some of the cool things we have in these drawers. If you are one of our on-camera schools, we're going to ask that you keep your mic muted until we're ready for our Q&A session in about 15 minutes, just so we can hear James a little bit better as he's showing some specimens. If you are not going to be on camera, you can go ahead and with your adult or your teacher or however you're managing your computers, type those questions you have in the chat, and I'll be fielding them and giving them to James so that we can answer some of them and see some really cool stuff. So without further ado, hi James, what can you tell us about where we're at right now and what you do here at the museum?
Wow, well, thank you so much. Well, first of all, we are, as you said, in the bowels of the museum. And this kind of antiseptically white room is one of the places that we store the archives of Earth and human history. And museums have nooks and crannies all over the place where they store these items. And why don't we get a sense for where we are right now? First of all, let's look down at the floor. And I know the floor isn't the most interesting thing, but this floor has special railroad track-like features in it. And normally, these cabinets have doors on the bottoms. We've taken these off for the purposes of today's engagement so that you can see what's in them and we can get in and out of them more readily. But I'm going to come right over here, and it turns out all these huge cabinets are like giant moving racks that you'd see at Home Depot or Costco or your gigantic store down the street. And they've got rollers and wheels and pulleys in them that allow to roll on these railroad tracks so that we can compact them and store even more stuff in the bottom of the museum here. This is called compactorized storage, and a lot of museums, libraries, and other archives use it to very carefully place items down below the surface of the earth and stack things up as tightly as possible to archive them for society. And so I'm one of the folks that helps with archiving this material. I'm what's called a curator. And in museum speak, that's basically a scientist. And so part of what I do is I do outreach. So I reach out to the public, whether it be you or helping with an exhibit or answering questions for a neighbor or even just doing a broadcast of sorts. Another thing I do is I'm a scientist. So in my case, I use rocks, minerals, meteorites, fossils, chemistry, and other structures to tell about how our planet has changed through time. And I use all of those tools, kind of like a detective uses clues, to decipher our planet in deep time. The last thing that I do as part of a museum is I take care of collections, and we're sitting in the collections right now. And these aren't my collections or the museum's collections, they're your collections. And we're shepherding them for you as custodians, in my case, of Earth history. And so one of the cool things about our collections here is that we've got big stuff and little stuff and black stuff and yellow stuff and even stuff that's really, really thin and flaky, like this giant piece of mica. And so to get things going, I'm thinking maybe we should take a poll. And I also want to just acknowledge that Tim and Kim are behind the camera and behind the scenes here helping make this happen. So thank you for your help connecting all of us from all over the world. Tim, do you want to give a poll to talk about what exactly is in museum collections and why is it there? Okay, everybody get out your joystick or your mouse or your touchpad or whatever your device is, or you can just use the Force because yesterday was May the 4th. Be with you, by the way. Today is Revenge of the 5th, for those of you that are Star Wars nerds, not saying that we are. But hey, take a look at this poll. Answer these. We've got about 30 seconds. Tick-tock. How do we decide what goes in a museum? What kind of stuff is here? I think it's all cool, but does that mean we should keep it?
So students, if you are not on individual computers, you can have your teacher maybe collect your votes as a class and put your answer in the poll. Take another couple seconds and answer if you haven't yet. Alrighty, and let's go ahead and see some of those results. How'd they do, James?
Oh my gosh, everybody out there is perfect. I love it. You guys all get an A. Teachers, remember, they're all getting A's for today's exercise. 100% love it. Although we'll probably have to have another quiz question later, right? Just in case.
For sure.
Anyways, so it turns out that museums have lots of different stuff in their collections, but it isn't just like we put anything in here. Almost all museums and archives have things that sort of fall into 4 separate categories. The first one is items that are useful for research, that is to understand about, in our case, our planet, right? And so those are items that someone might write a scientific paper on or use to discover something. The second thing that goes into museum collections, or sort of broad category, are things that might be historically important. And so something that might be historically important is something that, for example, maybe is from a mine or from a historic residence or from a people. It depends on whether you're talking about anthropological artifacts or zoological, or in our case, geological. Something that has some historical importance, right? Might not have a lot of scientific value, but we can never get one of those again, and it was very unique. Like, for example, a piece of the original building, one of the original buildings of Colorado, right? Before it was destroyed. The third thing that goes into museum collections is stuff that's of high educational value. That is, you can learn something from it and you can teach people with it. Why don't we, in just a second, take an example? Do you guys want to look at an example of each one of these? That's what I thought. So these are items that would be educationally useful. And the last thing are things that are just wow, eye-popping, jaw-dropping, stroller-turning items like the head of a T-Rex or a totem pole or a crystal that looks, here's an example of one of these, like here's one of these Elbyite crystals. You know, these crystals look like they came from another planet. And these are just super huge and cool. And so this is an example of the fourth category, something that is just wow, one of these blue-capped, unbelievable tourmaline crystals known as Elbyite that looks like it's got every color that you've ever seen in a Jolly Rancher. And what we really want to do when we have this, if you're a geologist, is you almost want to lick it. You know, it's like, does it taste like blueberry or raspberry or maybe strawberry or watermelon? In fact, some of these are actually called watermelon tourmalines in places because they look like the different colors that one sees in watermelons. And so these are items that are falling into that last category. They may not be historically important or necessarily scientifically useful, but they're really pretty and they're attractive. We can use them to tell a story about, in this case, minerals forming deep below the mountains of Colorado and other places. Do we have enough time to take a peek at a few of those other categories of items? Because, you know, people often ask me, like, what do you do as a geologist? And I always say I'm a detective in deep time, right? And so I'm using clues from other planets sometimes, and often from rocks, minerals, fossils, and other things to decipher Earth history. So let's find an example of something that might be historically important here. And I'm gonna look around here. I think we have one example in one of these drawers from a long time ago. And let's see, we got an example from Wyoming. Where is this? Here it is. So here's a specimen, has no scientific value. It's not a wow specimen, and it's not really that useful to teach with. But this is a piece of a sign that's made. Hey, guess where this is from, everyone? I knew you were all going to get an A on this. From Wyoming, with representative examples of the different types of jade or nephrite that are found in Wyoming. And nephrite or jade is or its varieties, jadeite, are a type of mineral that are used widely in jewelry and other elements. It's also built this is also laid down, this sign, this historic sign, on a piece of Yule marble, which is the state rock of Colorado. And so we have this piece in our collection as a representative example of a sign from back in the day. This is actually, oh my gosh, this has been in here for almost 50 years. And so this is an example of the historic elements in our collection. Whereas, for example, oh, here's one. Here, we're going to feature this specimen from Wyoming. This is an example of a petrified tree or a log, and I'm just going to walk a little closer. And this is an example of something that actually fits more than one category. In this case, this is a specimen that has high research value. It's kind of pretty. It's kind of bluish colored. This is a fossilized tree that has cracked down the middle as it dried up, and then had all of its cellular structures and features replaced by a variety of the mineral quartz, which is sometimes called agate or other things. And it's the same mineral that makes up glass or your reading glasses or things like that. And what's cool about this specimen is that you can actually see the rings of growth of this tree that it laid down every season from each year of its life. And so this specimen, this isn't just any old petrified tree. This thing's over 50 million years old. So scientists can go to specimens like this and literally read the tree rings, just like they do with a modern tree, to determine how wet and how dry, or what the climate was like, in this case, in ancient Wyoming, and compare it to today. And so this is one of these examples that fills more than one of those categories. It has a research story, it's pretty, and it's in our collections and available for use. The last kind of collection we have, and I'm going to open this up to questions in just a second, are things that are of high educational value, and they tell a story. And I don't know if I should show this one or not, but this is kind of a special piece. These are two rocks that, believe it or not, were cut up by someone to use as bookends. And these are from a concretion in Wyoming, and they were cut up to use as bookends. And they are beautiful as bookends, but they have super educational value, because it turns out that these aren't just any old bookends, but I'm going to have to set one of these down here for just a second to show you this. But a colleague of ours discovered that these were actually part of a coiled shell called an ammonite. And these are the minerals or septarian nodules and growths that formed inside that coiled shell when it died 100 million years ago. And so this specimen is, and ones like it, have oftentimes been used on geology and paleontology exams to figure out how did this form. Because it isn't, when you look at one side, it looks just like a bunch of cracks in the rock. But when you look at the other side, it tells the story of how it formed. And so those are examples of the 4 different kinds of collections we have in brief. And I bet you have a lot of questions you'd like to ask us.
Yeah, so on that note, we're going to go ahead and start opening our question and answer session. So I think Bridges Elementary, we went ahead and did a camera test with you earlier, but if you'd like to unmute your mic and jump on screen. Hello, hi Bridges Elementary. Awesome. So I'm going to have your teacher, Ms. Hammond, go ahead and kind of help navigate who is asking questions. And my biggest request is that you are just nice and clear and loud so that we can hear you, because remember, we're way underground right now. So, all right, what's your question?
So if diamonds are super hard, how can people
get a little closer?
Like cut into them and shape them?
Question is, how can we cut into and shape minerals? Yes.
Get a little louder.
Well,
Sorry, I'm sorry. Say it a little bit louder, Kennedy.
So if diamonds are like the hardest rock on Earth, how can people like cut into them and shape them?
Oh my gosh.
Such a good question.
That is such a good question. That's kind of like the chicken before the egg. Well, the answer is it depends, because some minerals actually can be really hard, but also kind of brittle, right? So they fracture along certain faces. And the real answer is that we often don't slice a diamond open. I guess you could slice a diamond with a laser, of course. Wouldn't that be cool to have a diamond cutting laser? But oftentimes we grind away the surfaces with other hard minerals, right? Do you guys want to see
I
some
was going to
diamonds?
say, do we have
my
diamonds? Should we,
Let's
should we
go
show
look at
them?
this. Now, I don't think I'm able to cut these here, but it turns out that Colorado actually has a diamond deposit. And so diamonds can have lots of cool shapes. I'm going to try to pick some big ones here. So these are some diamonds from South Africa, and these look like dice.
Wow.
And these illustrate two of the common shapes that you see in diamonds. One is a cube, right? And the other is basically like two pyramids glued together, and that's called an octahedron. Octo because they're two four-sided pyramids, so there's 8 in total. And so these are naturally occurring diamonds. These have not been cut or polished. This is how they came out of the earth. Kate, if you're willing to hold these for just a second,
Sure.
I'm going to go get one of the rocks that oftentimes contains these. This is a rock called a kimberlite.
Ooh.
And if we work together, maybe Kim can zoom in and show these diamonds. So these are diamonds in their natural state. Here's a diamond in this rock. And you can see it has its own what's called cleavage and crystal structure. And that's how they naturally occur. When we grind them down, we then want to maybe make them into shapes that will eliminate inclusions or impurities that are in them, and that might reveal their brilliance. And I'm just going to bring out this amazing piece of jewelry here. These are all real diamonds. This was something that was donated to the museum quite a while ago. And so these are diamonds that the surface of which have been sort of faceted. In other words, had little edges rubbed off of them. And I'm going to rotate this a little bit, but you see how it's kind of brilliantly reflecting and glistening? And so these are all diamonds that have been cut. And so this is the sort of after, those are the before. And what most people don't know is that diamonds come in a lot of different colors.
I was just going to say, in fact, I saw that in the chat. Someone's like, what causes different colors? So what does cause these different colors?
So color in crystals in general can be caused by a lot of different things. It can be caused by different ways that the structure or the elements, the building blocks of the minerals are arranged. And I'm just going to give an example of those. So if we come over here, so some minerals are arranged, they form a flat structure. And so this is mica. This is a mineral that's pretty common in granite and other things. And this mineral is flat as a pancake. In fact, it has lots of little sheets that can peel off like pieces of paper. And so its building blocks are arranged in kind of plates. Other minerals might form shapes that are kind of blade-like. And this is an example of a different mineral here. This is selenite or gypsum, and it forms a little blade that has pointy tips and is kind of knife-shaped in cross-section. And the shape, these have not been polished or cut. These are the natural shapes of the crystals that form based on the arrangement of the atomic structure. And that impacts the way light passes through it or reflects off of it, or in some ways is distorted by it. Another thing that you may have seen in this crystal right here in the middle is that there are sometimes impurities in the rock or other substances, and those can also make that turn a different color. And a good example of that is this amazing mineral here. Let's pick out this specimen here, which is known, this green mineral is known as malachite. And malachite is this green mineral, and the blue mineral next to it, I'm going to rotate this. So here's the green mineral. The blue mineral is called azurite. And what most people don't know is this is the same mineral as a clam makes its shell out of, calcite, except that you add a little bit of iron to it. And you add a little bit more iron impurities, you form green minerals like malachite. If you add a little bit more iron as well, you can turn it blue. And so there are lots of different reasons crystals have different colors, but those are a couple of them.
Wow, that is amazing. Okay, well, what an amazing question that sent us on like a neat journey and inspecting some cool specimens. So Thank you from our friend in the audience there. What are some other questions from Bridges that we can maybe find specimens to answer?
A little closer.
So, I also have like a rock collection at my house, and sometimes I like most of these I like bought or like someone's given to me. Like, so how do you like acquire some of your specimens and collections?
So that's a great question. How do we acquire specimens for the museum? Well, we acquire them in several ways. One way we acquire them is if someone donates something to us. For example, we've got some specimens in here. I'm just going to set this one down over here that people have donated to us that are pretty special. So here's an example of one right here. This is the mineral gypsum, and a lot of times this is the same mineral that's in drywall. It's kind of clear. You can see where there are impurities in it down here. I mean, check this out. So sometimes we get specimens that are donated to us by people that had a collection like you and want to give it to us when they pass away or they don't need it anymore. Sometimes we get collections that come from other institutions that maybe are not doing as much collecting or archiving of specimens. Sometimes we get collections because we go out and collect them ourselves, right? So we might go out and, for example, I was doing field work just 2 days ago down near Colorado Springs, and I was collecting rocks and fossils and minerals for a scientific project to understand how Colorado changed after a giant asteroid hit the planet 65 million years ago. And some of those specimens that I collected might end up in the collections here. Another way that we acquire specimens is sometimes we purchase something, right? We see something and go, holy guacamole, that's amazing, we have to have it, right? And so we'll actually go out and collect, purchase a specimen. And let me see if I can find an example of one. Well, actually, one of these is a good example. We didn't, oh wait, no, here's an even better example. So we might go out and purchase something like this when it becomes available. And oftentimes the community will let us know, oh my gosh, there's this incredible discovery, would you like one? And the people that are finding it invested a lot of time and money and effort to discover it, and so they want to be compensated. And so here's an example of the mineral rhodochrosite. And this is another little secret, kind of like the same mineral that clams make their shell out of calcite, which is usually white, but with a bunch of manganese in it that makes it pink or red, right? And this is actually our state mineral. And so this is part of a suite of specimens that we bought actually with the support of the community. Sometimes people donate money to help us acquire specimens. Sometimes we write grants. Sometimes it comes from other sources or foundations. But sometimes we'll acquire specimens by purchasing them to put into collections. And then the last way we get collections is sometimes by accident, where someone is widening a road or digging a pit for a housing development, and they'll find something and we'll go acquire it there. So there are probably a few other ways we get collections, but those are the major ones.
And just to clarify, because I see this is such a good example, I feel bad. The lighting in here is not what it should be, but this is a really, really bright crystal, everyone. So why is it this color? What causes the coloration in rocks and minerals like this?
So in this case, this is basically manganese being added to the mix, if you will. Okay. And if you add other elements to this, it'll turn actually a different color. It's a little bit like a close cousin to that malachite and the azurite, the blue and the green minerals I showed you earlier. And this is a unusual crystal. This is its natural shape. You can see the little steps on it. It hasn't actually been faceted. This is how it grew in rock. And this came from what used to be an old silver mine right up there in the mountains of Colorado.
Wow.
And it's such a cool looking rock that people made it our state mineral, and folks love to collect this.
Why not?
But it's actually a pretty soft mineral. Like you'll rarely see rings or bracelets made with it because it's easy to bang it up. So if you do see it, it's usually as a stone or maybe in a brooch or earrings or a pendant or the like.
Very cool. Well, two questions answered in one. Thank you for sharing it. What's another question from Bridges? Let's go ahead and hear another. Oh, Bridges Elementary. There you are.
Here we go.
Do you guys have a obsidian, and if so, how does it form?
Oh, yes, we do. So obsidian, the question is, do we have any obsidian and how it forms? And we sure do. And I think there are a couple of pieces over here. And I'm gonna see if I can find one. Here we go. So this one is kind of fun. This is a piece of obsidian from Wyoming, but it's not just from anywhere in Wyoming. This is from Yellowstone National Park. And Yellowstone is, of course, one of the most famous, and if I'm not mistaken, it was the first national park, but we should look that up to be sure.
It's true, it is.
But this is a rock that's kind of glassy and what's called vitreous. You can break it in what's called conchoidal fractures, so it makes these sharp edges as it breaks. It's been used for millennia as implements, whether they be cutting tools, ooh, wow, that's pretty sharp, or piercing tools, or axe heads or arrowheads or the like. And so the reason it has this structure, ooh, Kim, I don't know if you can zero in this, you can see this little conchoids right here. See the little circles? Glass breaks just like this. And that's because this is volcanic glass. So when lava spews out from a volcano onto the surface of the earth, if it cools really quickly, it will oftentimes form obsidian. And that's because it's cooling so fast that the crystals, the ingredients in that lava, don't have time to organize one another and grow into larger crystals. And let me see if I can find a piece of granite or granite-like rock over here. Okay, this is not a bad piece right here. Here we go. So this is this specimen is from Texas, but this is basically a granite. And you can see it has kind of a salt and pepper shaped texture to it. It's got black minerals and pink minerals and maybe some shiny platey ones in here. And this is the kind of stuff that might be made into tiles or countertops or whatever. And this is another kind of rock. This is what happens when lava bubbles up from the bottom, from the center of the earth or from the inner parts of the earth up to the surface. And kind of like a zit or a boil, it doesn't quite make it out on the surface. And as a result, that lava, underground lava, by the way, is called magma, cools really slowly. And all the particles in it have time to organize and form these larger crystals. And I think I showed you that piece of mica earlier. Well, this rock has microscopic pieces of mica, just like this giant slab I showed you earlier. And the reason we can see those is because they had time to grow. These crystals didn't. So lava that spewed out quickly, lava that got stuck on the way up and had to cool really slowly.
Wow, great question. You sound like someone who maybe has interest in volcanoes or rocks. So that was a great one. Thank you. What's another question from Bridges Elementary? Let's go ahead and snag at least one more.
So which of your rocks was the hardest to obtain, like the most hassle?
Yeah, which rock or specimen is the hardest to obtain? And and I love that because someone in the chat asked a similar question of basically like, how far do we have to drill down to look for them? How are we finding these things? Great question.
Yeah, so can I answer kind of with a kind of funny answer? So it turns out that the hardest to obtain rock is one that we don't have yet. And it's a piece of Venus. I want a piece of Venus for our museum. And I want to be the first museum in the world or institution to have a piece of Venus. Because planets are made up of rocks, right? And there are pieces of planets that basically get knocked off like billiard balls hitting them, and they jettison out little pieces of rocks that become meteors, or in some case asteroids, depending on their initial origin. And those pieces are floating out in outer space, and every now and then they come down to the surface of the Earth. And so if you've ever seen a shooting star, you know that actually shooting stars are just pea-sized or dust-sized particles of rock that are coming into our atmosphere and are burning up as they come in at thousands of miles an hour. But sometimes bigger pieces of those make it down to the surface and explode, and they might form a crater or whatever, and we call those meteorites. And it turns out that there are actually kind of 2 or 3 broad categories of meteorites out there.
Don't we have meteorites? We might even have one from like a planet, a recognizable planet, right?
We do. In fact, we have meteorites that were bounced off of Earth, went out into outer space, and then came back to our surface. And we even have some very small pieces of meteorites from Mars. There are hundreds of pieces of meteorites that are unusual, and they have a chemistry.
Should we show them?
Do you guys want to see that? Or
I don't know.
Okay, here we go.
Let's do it.
We could give you a PowerPoint presentation with lots of bullet points. Okay, let's skip that. So first, meteorites. These big blob-shaped rocks are part of a meteorite collection. And these things are ugly, ugly-wuggly. Check these things out. I mean, who would want to collect this? This is just like a big brown blob. But this is a big brown blob that's kind of special because it's about 4.5 billion years old. And actually, this is a piece of the type of meteorite that we use to date our planet itself, because all the old Earth rocks have been recycled by mountain building and soils growing on them and rivers washing them down. So the only really old records of early planets are actually floating out in outer space as asteroids or meteors. And we get records of that early Earth and early planetary formation from those little pieces of debris that fall back down to our surface. And this is an example one of those. It's kind of sculptured and has these little scoops in it that form as this thing basically melts and evaporates almost as it's coming in at super hot temperatures. It forms this crust on it. This crust is called a fusion crust. It's like the crust that forms on a cast iron pan when you heat it really hot a bunch of times. And so we have lots of examples of these bodies from other places. And most of these came from Earth or early planetary formation. But we are fortunate that we have a couple of samples. In fact, they're just thin little slices of some meteors that came from Mars. And so these are a couple of thin slices of rock that fell in 1962 in Nigeria, and that have minerals in them and structures in them and chemistry in it that's unlike almost all average Earth rocks and unlike rocks from the moon, which we have samples of, but are very much like what we expect Mars to be like, one of our cousin planets. And you can see this is just a little slice. This little kind of faint looking rind on here is the edge of that burnt fusion crust of those other meteorites I was showing you, which are all from sort of an Earth-Moon type system. And so this is an example of a piece of Mars. Isn't that awesome that we're holding a piece of Mars in our hand? You want to hold this? Get the vibrations. Yes. And the reason I said the hardest to get rock we don't have yet is because there are not any yet documented Venusian or meteorites from Venus. There are some that are like, might be like Venus, it might not. But someday someone is going to find a meteorite and it's going to have minerals and chemistry and an age and other structures in it that are unlike any of the Martian meteorites and that are unlike any of the Earth-related or Moon-related meteorites. And it'll be the first physical evidence from that planet. And if you find it, call us.
I was going to say, I hope it's one of our friends in the audience today, because I want you to call us and so that we can also investigate it with you. That is so cool. That we have a piece of Mars in our museum, everyone.
There's a couple of pieces actually on display. We opened a new space exhibit called Space Odyssey about just actually over the pandemic. And with the help of a donor, we were able to acquire a couple of really nice pieces of Martian meteorite that are whole.
Very cool.
And much bigger than this. And they're actually on the display upstairs, so if people want to visit. There's also a meteorite that fell through someone's roof of their garage down in Canyon City, Colorado, along with a big hole in the garage. And luckily they weren't in the garage at the time, so they didn't get hit.
Scary. Very cool. All right. Well, that was amazing. Thank you, Bridges Elementary. Those were excellent questions. We're going to go ahead and turn to the chat and take just a few of those, see what other specimens we can round up to answer those before we end today's program. So let's see. I don't know if you want to set down the pieces of Mars, but
I'm going to go put Mars back in the cabinet. I don't want to
Back
lose
in the
Mars,
box.
right?
Cool. Okay, so we have a couple questions. We have some questions about, let's see, it looks like diamonds. And I know we saw a little bit of diamonds earlier, but the question is, how do we know if it's like a green diamond versus an emerald or a blue diamond versus a sapphire? How do you determine different rocks and minerals and gems?
So that's a great question. So one of the ways that you can tell is based on the shape, and I'm going to go over here and see if I can find quickly some emeralds and some sapphires. There's a small one. Here we go. Here are some sapphires. Here, and what was the other one? The bigger one that's going to show up on camera. Why don't we just pick these sapphires for now, and let's pick a fun one. Let's pick this. These aren't in either of the question. So one of the ways we can tell is based on the crystal shape, right? And I'm going to lay these on my hand, and hopefully we'll be able to see them. So these are a bunch of faceted or cut stones. So we can't really use the shape in these to determine what they are, but these are sapphires. So we can use the color, we can use the chemistry. So it turns out that you can take certain wavelengths of light or radiation and bounce it off or pass it through a mineral, and it will fluoresce, which means it will radiate back out a little bit of light, or it will bend or reflect that light in a distinct way. And so diamond, for example, does that differently than does ruby or sapphire, which are both kind of cousin gemstone or minerals. And we can't see that with our naked eye. The shape is also something that you could tell with your naked eye if you were in the field or a mine. And I'm going to use this crystal to illustrate that just because it's a fun one. So this is aquamarine, which is basically a long prismatic mineral. This is our state gemstone in Colorado. And it's kind of a long mineral. This has not been cut or faceted. It's kind of an aqua blue, but these can come in kind of clear and other shapes. And I'm going to point it on its end now. And so on its end, you'll see that its end is actually flat and has 6 sides. And so that is one of the ways you can tell that you have this particular class of minerals, because some of the other ones, like you notice there's these purple minerals on here. Those are fluorite, and those form little cubes. They can be purple, yellow, they can also be aqua. But that mineral, because of its atomic structure, the sort of ball and stick, if you will, figure or internal Legos of it, only typically makes, not only, but often makes cubes and doesn't make these long shapes.
Cool.
So those are a couple of the ways we can tell different minerals and colors based on the naked eye, and then also based on different wavelengths of light and chemistry and other features.
Is hardness one of the factors too? Someone asked about like diamonds,
Yes.
like what's the hardest diamond or?
Diamond is the hardest, but there are other minerals like garnet, which is what you see in sandpaper. It's this sort of orange colored mineral that's actually pretty hard too.
Cool.
These minerals like fluorite is actually pretty soft. Sapphire or corundum is actually the second hardest mineral after diamond. And so there's this sort of a bunch of tests that geologists do, scratching minerals or seeing what their powdery streak is. There are even some minerals that we drop acid on because they fizz, like calcite or aragonite or malachite or things like that.
Very cool.
Yeah.
Well,
and they'll
thanks for sharing
fizz,
those.
right? Whereas quartz won't fizz,
Yeah.
for example, even though they look very similar.
A lot of cool ways to test rocks and minerals. I had no idea. That's amazing. So kind of last one, I want to summarize a number of questions. We have requests and interest in fossils. Do we have any fossils that we could show?
Oh boy, we have lots of fossils. Most of the fossils that we have, here, I will put this away later. I'm just going to sit this here. Most of the fossils that are accessible right now, did I already pull out a piece of wood?
We did, but actually someone wanted to know, does it still make oxygen if it's petrified wood?
No, it doesn't. So, plants basically take carbon dioxide and in the presence of sunlight and with a little bit of water, they make their tissues. So they make wood or leaves or other stuff. And then they, if you will, breathe out, or their waste gas, usually coming from the bottom of the leaves, is oxygen, right? And bacteria that are photosynthesizing, or that process called photosynthesis, also does that too. But once they are petrified, they don't do that anymore.
Bummer.
And just for fun, if people want, I can pull out. We have lots of petrified wood that's pretty fun. Here's a piece that's from the Medicine Bow Range in Wyoming, and this one has the impressions of the bark. And what I love about this one is it sort of tells the story of a squashed log, right? And you can tell that the log decomposed a little bit before it got fossilized because it has a hole in it.
Wow, that's
like
pretty
a giant downward hole. Oh, and look, and there's still some debris in there. One of the things we do at museums, by the way, is when we get collections that might have soil in them or been sitting in a garage or in the field, sometimes we'll freeze them and then thaw them and then freeze them again, because then if there are any spider eggs or larvae of insects in them, they don't then decide to come out once we put them in the collections and crawl over to zoology and eat the stuffed birds in the Native American baskets.
Yuck.
but so don't worry, we've taken care of this before we put that in there. And I love this because it reminds me of the bark of a tree.
It feels like a tree.
From, in this case, tens of millions of years ago.
Wow, so cool. Well, that's amazing. That was a great.
If people want to see more fossils, there is a room about 8 times this size downstairs that is full of fossils.
It's true.
We only have a small number in this room.
I know. Yeah, it sounds like everyone's going to have to come to the museum for sure, because we've got a lot. So, all right, because we only have a few more minutes left, I think for our last specimen of the show, why don't we throw that last poll? Because we want to know if you want to see something pretty, something unique, something extreme, or something found locally. So real quick, take a few seconds. We're going to choose one last specimen to show and tell today based on your responses. All right, and let's go ahead and see what the audience is looking for today. It looks like we want to see something extreme. We had some answers for each, but do we have anything extreme, James, that we could maybe show off?
Extreme. Let's do extreme in 2 ways.
Ooh.
Let's do extreme in deep time. Let's do extreme in outer space, and let's relate it to your very own planet. How does that sound?
Can't say no to that.
So one of the things when I think about extreme is I think of Jekyll and Hyde or dual personalities. And there are actually some meteorites that are kind of extreme in that they can't really decide what they are. So a lot of meteorites are actually made out of metal, and or a portion of them are made out of metal. And you can take a magnet like this, and we always keep these around. They're really handy. They're also good for erasing your disk drive. If we're mad at you, don't worry, we won't do that. And you can stick them to a meteorite and they'll stick. So a lot of meteorites have metal in them, and those are called nickel iron meteorites. And those meteorites are very much like the core of our planet. But some meteorites, are you willing to help me with this for a sec? Maybe hold this, just come over here and just hold this for a second. I'm going to go grab another specimen if you can hold that one. Other meteorites are more like Earth rocks, in that if you cut them open, and here's a meteorite that, let's look at the edge of it. These both have that fusion crust where the meteor has been burned on the edge. And this one's more like an Earth rock. You can see it has a little glints of metal in it. It's also a little bit magnetic. But it's mostly like an Earth rock, kind of like the rock type that might form when a volcano oozes out on the surface of the Earth and forms a rock called basalt. But rocks are funnily made out of minerals, and fossils and other things. And the most common mineral on Earth is this mineral called olivine. And most of our planet is made up of variations on olivine. Sometimes when people carve olivine into a gemstone, it's called peridot or peridot, depending on how you want to pronounce it. And this is a meteorite that's billions of years old that has both the nickel iron that's like the core of our planet and these minerals, olivine or peridot, that are more like the outer skin of our planet and like volcanic rocks that you might see on the surface of today. This is called a palisite. And so this is kind of an extreme because this meteorite preserves parts of minerals and rocks that you'd only find in the hottest, highest pressure, craziest, most insane place on Earth, our core, places that only Jules Verne or Bruce Willis can get to. And it also preserves the most common mineral that's also really pretty, and maybe some of your birthstones, this is actually my birthstone, that are really common on the surface of the planet and are actually quite beautiful.
Wow, what a combination. That is so cool. Great find. I'm so glad everyone chose extreme. Otherwise, who knows? We wouldn't have seen this. So thanks. Very cool. Well, on that note, friends, it's probably about time that we wrap up. Unfortunately, I wish we could spend all day, and let's be real, it could be all month. There's a lot of cool stuff to see in here. So I love that everyone tuned in today. We have just had the best time showing you everything. If you had fun today, we hope that you come visit us at the museum or join us for future broadcasts. Thank you again to our on-camera schools. We loved your questions. Thanks to the on chat questions as well. They were amazing. So next fall and school year 2022, we will start up again with more broadcasts. So teachers, students, please feel free to join us. We'd love to see you again. Thank you. James, do you have anything you want to end the note on?
You know what? Every one of us has the secret ingredient that makes a scientist great, and that's curiosity. And so I'd say pursue your curiosity.
Yeah, and when you find that, I think Venus rock, was it? Please let us know. We want to know. So cool. All right, well, have an amazing day, everyone. Thank you again for tuning in.